volumetric expansion or cubical expansion. Means by absorbing heat, if the volume of the material altogether is increasing, then we say there is volume expansion or cubical expansion. So here we consider a sphere. For example, if I take a sphere of initial volume V and by heating it through a temperature delta theta, its volume altogether is found to be increasing. Volume altogether increases through delta V. So V is the initial volume or original volume. Delta V is the increasing volume obtained by an increasing temperature of delta theta. Then by applying the conditions using the inferences we made, that the increase in volume is directly proportional to original volume. First inference. Second one is that increase in volume is directly proportional to increase in temperature. Now, we have therefore increase in volume is directly proportional to volume into increase in temperature. So delta V is equal to gamma into V into delta theta. So this is the equation we are having for volume expansion, where gamma is called coefficient of volumetric expansion or cubical expansion. Gamma, coefficient of volumetric expansion. Volumetric expansion or cubical expansion coefficient. Both you can choose. Now what it is, you can obtain from this one that gamma equal to delta V by V into delta theta. That means that coefficient of volumetric expansion is defined as the ratio of fractional increase in volume to the increase in temperature. That is fractional increase in volume by increase in temperature. Here also you can see the unit of gamma as per degree Celsius or per Kelvin, depending upon the unit used for measuring it. Or unit used here for the temperature comes as what we call the unit of coefficient of expansion. Now, as earlier, we can see this equation rewritten in terms of initial volume and final volume. For example, if Vi is the initial volume, increases to a total final volume as Vf. When temperature initial increases to temperature final Vf. Applying that criteria over here, we get delta V will be final volume minus initial volume. That is equal to gamma into initial volume into final temperature minus initial temperature. So this can be rewritten as the final volume of the material is equal to initial volume into 1 plus gamma into theta final minus theta initial. These are the equations we can have. for the volume expansion, this one and this one. So note it down properly. So we got the equations for expansion, linear expansion, superficial expansion and what do you call it? Volumetric expansion. Then if you watch these equations all, I will be taking all the equations together now. That is the equation for linear expansion was what do you call L final is equal to L initial into 1 plus alpha into theta final minus theta initial. Okay. Then surface area final will be equal to surface area initial into 1 plus beta into theta final minus theta initial, and this is the volume expansion. Now you can see that in all the three cases we consider that theta final is greater than theta initial. This is the condition we have considered in all the three cases. That means this difference comes as positive and therefore the volume will be increasing. Now suppose that if we take the final temperature, for example, the theta final is less than theta initial. For example, suppose 50 degrees Celsius and this is 100 degrees Celsius. So initially the object is at 100 degrees Celsius and finally it is at 50 degrees Celsius, means there is a decrease of temperature is coming. So when that condition is substituted in these equations, you can find that this part will be negative. And this negative comes over here, and by applying this particular case, we can see that all these will be becoming what you call minus, minus and minus. So because this difference is minus coming. So what happens if minus sign comes over here? Because of this minus sign, you can see that the dimension, final dimension goes less than the initial dimension. That means there is a contraction is taking place if that is the case. Understood? So the same equation, you just substitute for the change of temperature, and if that change of temperature is positive, expansion happens. If that change of temperature is negative, then what you call contraction is coming in that single equation itself. Okay? So understand the situation, whether it is expansion or contraction, depending upon that, you will be that depends on what we call the increase of temperature or decrease of temperature. So this fact is very, very important. Another fact to be noted is that you came across what we call three coefficients of expansions, alpha, beta and the third one is gamma. So all these three are representing coefficient of expansions only. One is linear, other is superficial and the third one is volumetric. And they are having the same nature because all the three are having the same temperature, the unit either per degree Celsius or per Kelvin. So their nature is same. So are they equal or different, or is there any relationship between these coefficients of expansion? This is what we are going to see in the next video, and that part is very, very important. So in all these three videos we understood linear expansion coefficient, linear expansion, superficial expansion and the third one volumetric expansion.